I'm going to read the words to you. You can follow along if you click that last link I sent you. A blood test for a disease shows a positive result in 98% of all cases. So let's say that D is having the disease. And I think he used T in class. Let's say T is a positive test. That would mean that D complement is you don't have the disease. And T complement is a person tests negative for the disease. Okay. So here's what, so it's really kind of good to practice being able to read something and interpret into what the notation is kind of going to look like. So a blood test for a disease shows a positive test result in 98% of all cases when the disease is actually present. So we're saying, given the disease is present, the probability of a positive test is 98%. So the probability of a positive test, given that the person has the disease, is 98%. Okay. This problem also says it's also the probability of a positive test result is 6% in the cases where the disease is not present. So the probability of a positive test result, given that the disease is not present, is 0.06. And we're being asked to find the also we know that the prevalence of the disease. So the prevalence of the disease, I shouldn't write this down. I should just write the probability. So the prevalence of the disease is 1 out of every 250 people. So the probability of just having the disease is 1 in 250, which as a decimal is 0.004. So we want to find the probability that, and then we're going to start off kind of simple. We want to find the probability that someone has a positive test. So what's the probability of a positive test? Well, for a lot of these problems, it's really kind of useful to make a tree diagram. So I kind of like to make my tree. So my tree diagram is going to be a little bit different than the one on the notes because I kind of like to write all the possibilities. So usually, not always, and there's actually a homework problem where this kind of doesn't ring true. Usually when you're making a tree diagram, the first branch of the tree diagram should be the thing that's given, right? You want to say, well, in these probabilities, it's given that you either have the disease or don't have the disease. So the first branch should be we have the disease or we don't have the disease. Right? Because then the probability after that is going to be the probability that you test positive or negative given that you have the disease or don't have the disease. And this probability is equal. So I should really say if the probability of having the disease is 0.004. And the probability of not having the disease is, well, it's 1 minus 0.004, which is 0.996. Okay. So that's the first thing, right? You have to have one of the two things happen, right? Someone either has the disease or they don't. There is no third option. Okay. And then from there, we either test positive. So we have the probability of testing positive given that you have the disease, or you test negative. So my picture is looking, I feel like this picture is not, let's make this a little bit nicer. Yeah, sorry, sometimes my trees look gross. So let's do it this way. So we can write things nicer. Probability of having the disease is 0.004. The probability of not having the disease is 0.996. And then for each of those, we have two options. We have the probability of testing positive given that you have the disease, which is already told to us, 0.98. And we have the probability of testing negative given that you have the disease, which must be whatever's left over, 0.02. The nice thing about each kind of branch here is that the probabilities always have to add up to 100%. Because because it's either this choice or this choice. And once it's one thing or the other, they have to add up to 100% because one of them has to be true. If you have the disease, either you test positive or you test negative. There's no inconclusive test results. Here, it's the probability of testing positive given that you don't have the disease, which we were told was 0.06. And then this branch is the probability of testing negative, given that you don't have the disease, which must be 0.94. Okay, so now we want to find the probability of having disease, which is just all the paths that get us to having the disease. So we could have this and this, or this and this. Those are the only paths that get us to having the disease. So the probability of having the disease, sorry, I said the wrong word there. There's nothing like, sorry, the probability of testing positive, right? These are the paths that get us to a positive test and to a positive test. So you can either have the disease and have a positive test, or you can have the disease, or you can not have the disease and have a positive test. So the probability of testing positive is going to be 0.004 times 0.98 plus 0.996 times 0.06. If we calculate that, it's going to be approximately 0.0638. So it looks like there's about a 6.38% chance of testing positive for this disease. Just if you pick some random person off the street. Which is interesting, right? Because there's only a 0.4% chance of actually having the disease. Whereas there's a 6%, almost more than 6% chance of testing positive for the disease. Okay. So sometimes I don't think let me quickly scan your homework assignment here. I'm just curious. Yeah. Sometimes people talk about testing positive twice. That is something we could do, but I don't feel like that's going to be quite as useful. So let me talk about something else. Let's say we have the same situation with one difference. I'm going to need to erase this because I guess I can erase this, right? Sure, I can erase this and write it again. It's not a big deal. So let's say we have the same situation. We have all this except for one thing that's different. So we know that the probability of testing positive given having the disease is still 0.98. We know the probability of testing positive given that we don't have the disease is still 0.06. But now instead of knowing the the pervasiveness of the disease, or what's the word? Sorry, I like what here. Instead of knowing the prevalence of the disease, not the pervasiveness, we know the likeliness of testing positive. So let's say I know that the probability of a positive test, I'm just going to make up a number here. Let's say the probability of a positive test is 20%. I want to know what's the probability that a random person has the disease. So this question is where, and there's a question like this, at least someone was asking about a question like this, I think on the homework or maybe on the worksheet. I don't remember where it was from. But the idea here is that you might think you should do things the other way. And I actually thought, I told it was like, oh, we should make a tree where we first start with, the probability of having a positive test. And then after that, we're going to have, right, the probability of the disease given a positive test and the probability of not the disease given a positive test. But the problem with this, there's actually a few problems. But one of the problems is we don't know either of those probabilities, right? We don't know. And yeah, you could use Bayes' formula to find them, but that's kind of doing way more work than we need to do. So the idea here is that to find the probability of having the disease, we're actually going to use the same tree diagram we used before. So we're going to say, all right, either a person has the disease or they don't. So here's the probability of having the disease. Oh, we don't know what that is. And here's the probability of not having the disease. We don't know what that is either. We do know that it's 1 minus the probability of having the disease. Okay. And then from each of these, we're going to go the same way. We know the probability of testing positive given that you have the disease is 0.98. And the probability of testing negative given that you have the disease is 0.02. And the probability of testing positive given that you do not have the disease is 0.06. And the probability of testing negative given that you don't have the disease is 0.94. So I want to find the probability of having disease. Well, here's what we're going to do. Just like last time, we're going to say I can find the probability of, well, in fact, I know the probability of having a positive test. I make it up, it's 20%. And it's going to equal the probability of having the disease times the probability of having the positive test giving you the disease, plus the probability of not having the disease times the probability of a positive test giving you don't have the disease. Let's see how that works out. So we can say that the probability of a positive test is equal to the probability of having the disease times the probability of a positive test given that you have the disease, plus the probability of not having the disease times the probability of a positive test given that you don't have the disease. And this is actually what we often call the law of total probability, right? This part right here, comes everywhere. This part right here is the probability of having a positive test and the disease. And this part right here is the probability of having a positive test and not having the disease. And that's all the ways you can have a positive test, right? You can either have a positive test and have the disease, or have a positive test and not have the disease. Those are the only options available. Okay, but then we know that the probability of having a positive test is 0.2. We don't know this. We're going to find it. We could call it X if we wanted to, or we could just leave it as the probability of having the disease. We do know that this is 0.98. Now, we don't know what this is, but we do know that it's equal to 1 minus that. Right? The probability of the complement of something happening is 1 minus the probability of the original thing happening. And then finally, the probability of a positive test given that we don't have the disease is 0.06. Now look, we have an equation and there's only one unknown, P of D. So we can actually figure out what P of D is equal to here. So let's see, I've got 0.2 equals 0.98 times P of D plus distributing the 0.6 there, 0.06 minus 0.06 times P of D. Subtract 0.06 to this side, so 0.2 minus 0.06 is going to be 0.14. And adding this term to this term, 0.98 minus 0.06 is 0.92 times P of D. So then we're going to end up getting the probability of having the disease is 0.14 divided by 0.92. And using a calculator, that's going to be, let's see, 0.14 divided by 0.92 gives us about 0.152. So about a 15% chance of having the disease. Interesting. Maybe. Maybe it's not interesting. I don't know. Well, it's kind of interesting. What is actually, so I will say, the Bayes rule, the Bayes formula stuff is actually the most interesting because In an example like this, in fact, we could even use this example. The probability of having a positive test given that you have the disease is 0.98. Whereas the probability that you have the disease given a positive test is very likely to be much, much less than that, which is really kind of interesting because people kind of make the wrong assumption sometimes and think, oh, well, if you have a positive test, it's pretty likely you have the disease. It really more depends on how prevalent the disease is in the world. That's kind of the bigger factor when it comes to determining what the probability is of having the disease, given that you have tested positive. Yeah. So let's see. I think we need to, we can look at that. Okay. So let's go ahead and now let's go to that example that I was looking at before. And again, I think it's going to be easier instead of trying to write the whole thing out. Again, where you can do it, you can go ahead and look at the document if you wish to. I can send the link again in case anybody didn't get it. Here's the, maybe I can. Here's the other document I'm looking at. So a rare disease affects one out of every 1,000 people. So we know that the probability of this disease is 1 out of 1,000. Okay. A blood test is positive 99% of the time when the disease is actually present. So the probability of a positive test, given that you have the disease, is 0.99. I suppose I should write this as a decimal. It's 0.001. The probability of having a positive test when you don't have the disease is 2%. So 0.02. So we're going to do all, so what we really want to answer here is what's the probability of having the disease given that there was a positive test. So the way I usually think about this is just like the usual conditional probability formula. Right? The probability of this given that is the probability that they both happen divided by the probability to test positive. Okay, we know how to find the probability to test positive, right? The probability to test positive is going to be all this, right? That's the formula for the probability of testing positive. And to be really, so I honestly would make a tree diagram still, right? So yeah, the tree diagrams are nice, I think anyway. So right, you can either have the disease or not. Probability of the disease is 0.001. Probability of not having the disease is 0.999. And then from there, you can either probability, you can have a positive test given the disease, which is 0.99. I don't actually really care about this other branch. And then from here, you could have the probability of having a positive test given that you don't have the disease, which is 0.02. And again, I don't really care about this other branch here, but it is there. And we might care about some other points. So it's right, it's good to still be aware that, oh yeah, there's another thing that can happen. You can either test positive or you can test negative. So the probability of testing positive is probability of having the disease times the probability to test positive and have given that you have the disease. Or some people like to write, it's the probability of having the disease and testing positive plus the probability of not having the disease and testing positive. And on top, we have this as well. Okay, but then the probability of having the disease and testing positive is just the probability that you test positive given that you have the disease times the probability that you have the disease. At least that's one way of writing it. And that's the way we want to write it because that's the information we have. And then the nice thing about seeing it this way is you might notice that this thing here and this thing here are exactly the same. So in fact, that there is also going to be part of your denominator. And then the other part of your denominator is the probability of testing positive given that you don't have the disease times the probability of not having the disease. And that's your Bayes formula. It's kind of it. So notice we have to find the total probability of having the disease, which is down here. And then we're dividing the probability of having the disease and having a positive test by that total probability of having the disease, of having a positive test. So what do we end up getting? Well, we have this times this. So we have 0.99 times 0.001 divided by the literally exact same thing, 0.99 times 0.001 plus this thing here, which is the probability of not having the disease, 0.999 times the probability of a positive test given the disease. So that's going to be 0.02 times 0.999. When you calculate this, you get about 0.0472. So although there's a probability of a positive test given that you have the disease of 99%, if you have a positive test, the probability that you actually have the disease is less than 5%. Very big difference in those probabilities. So it's very important, right? As he was saying in class, like from a doctor's perspective, right? You don't want to kind of conflate these because they have very different values and very different meanings. Right? If I went to the doctor and I took some test for disease and I came back positive, the doctor said, well, there's a 99% chance you have the disease. I'd be like, right? Where really that's not the case. There's probably a much lower chance of having disease. So typically, that's why you usually test twice, right? Like if you test positive the first time, they will often have you test again to see if you test positive again. Because if you test positive again, then it's very likely that you, well, I wouldn't say very, it's a lot more likely. So in fact, we can actually calculate that if you want. I think that is worth calculating. So let's look at that because it's kind of interesting. So what's the probability of having the disease given 2 positive tests? Okay, so that's going to be right. So I want to know this. I don't know that. Right. So I'm going to think of this as, well, again, right, I'm going to really just use Bayes formula again. It's going to be the probability of having the disease and having 2 positive tests divided by the probability of having the disease and 2 positive tests plus the probability of having the disease and, of not having the disease and 2 positive tests. Okay. Yeah. So I feel like let me see, the numbers here look a lot more interesting. Let's make a table. So I want to know what's the probability of having 2 positive tests, right? That I want to find this part here. So I'm going to make again a tree. So on the first branch, probability of having the disease is still 1 in 1,000, 0.001. Probability of not having the disease is still 0.999. And then from there, we branch off. And again, we are assuming these tests are independent. So what's the probability of having 2 positive tests given that you have the disease? Well, each test has a 99% chance of being positive if you have the disease. So that's just going to be 0.99 times 0.99. Right? Because there is no, right, there is no dependence. Each test administered is independent. And then we don't really care about this branch here. And in a similar way, the probability of having 2 positive tests, given that you don't have the disease, should be whatever that probability is squared, which is 0.02. So it should be 0.02 times 0.02. Well, great. We can totally figure all this out now, right? So the top part is the probability of having the disease and 2 positive tests. So that's going to be 0.001 times 0.99 squared divided by, same thing, right? That's the good thing about Bayes' rule, is that first thing kind of always shows up again. So you've got 0.001 times 0.99 squared plus the probability of having 2 positive tests and not having disease, which is going to be, probability of having not the disease and 2 positive tests given to be on the disease, which is going to be 0.999, which is practically 1 times 0.02 squared. And when you calculate this, you get about 0.71. So the probability of having the disease given 2 positive tests is significantly higher, right? Given 1 positive test, it was less than 5% chance you have the disease. Given 2 positive tests, it's over a 70% chance of having the disease. So quite a big difference. Definitely seems if you test positive twice, at least in this scenario, there's a very likely chance that you actually have the disease that we're talking about. Okay. Let's see. Yeah, let's do one more. Yeah, we do one more example, and then we can look at some other stuff. So the thing about Bayes' formula is it's all about kind of the order of things and switching order. So typically, right, you ask things like, like for cards, for example, what's the probability that the second card is something given that the first card is something? And Bayes' formula lets us kind of reverse the order. So Bayes' theorem, you can also think of as trying to find the probability of something that happened earlier. So let's look at this. We draw 2 cards. One at a time. From a standard deck, find the probability, from a standard deck, find the probability that the first card is an ace, given that the second card is an ace. Okay, we can do that. So we want to find, and let's label these as, let's say A is the first card is an ace, B is the second card is an ace. Now we want to find the probability that the first card is an ace, given that the second card is an ace. Okay. And so again, right, like we know, well, we can figure these out, right? We know that the probability of the first card being an ace, just in general, is 1 out of 13, or 4 out of 52, right? So let's make a tree diagram. So I should point out, you don't have to make a tree diagram. You could just memorize Bayes' formula. I like the tree diagrams. I think they're easier. So I'm going to say on my tree diagram, I have the probability of the first card's an ace is 4 out of 52, which is 1/13. Probably the first card is not an ace is 12/13, or 48 out of 52. And then the probability, the probability that the second card is an ace, given that the first card is an ace, is something we know how to figure out, right? Someone asked an interesting question in class, which I think is worth pointing out. Sorry, brain. First card's an ace, so we took one of the aces out. There's now only 3 aces left out of 51 cards, so there's a 3 out of 51 chance the second card is an ace if the first card's an ace. And then on the other hand, right, the probability that the second card is an ace, given that the first card is not an ace, so now there's still 4 aces left in the deck out of 51 cards remaining. There's a 4 out of 51 chance. Great, we have all the things we need. So I want to find the probability of A given B. I know that's the probability of A and B divided by the probability of B, which we can totally read from this whole thing. So the probability of A and B is all the ways you get to A and B. So A first, B second. Probability of A and B is 1/13 times 3/51 divided by the probability of B, which is all the ways of getting to B. So you can do this and this, or you can do this and this. Those are all the ways of getting to just B. So that's going to be a 1/13 times 3/51 plus a 12/13 times 4/51. So looking at these fractions, I noticed that every single one of the denominators is a 13 times a 51. So I have it divided by 13 and 51 here. I have it divided by 13 times 51, 13 51. So I could multiply the top and bottom by 13 times 51 and just get 1 times 3 over 1 times 3 plus 12 times 4, which is a 3 out of 51 chance. Which I feel like I'm making a mistake or not. No, that's right. Yeah, that's all right. Which reduces to 1 out of 17. Although I feel like 3 out of 51 is a more useful way of thinking about it, right? Because you're saying if you know the second card's an ace, you take one ace out, and there's 51 cards left. There's a 3 out of 51 chance that the first card was an ace. Interesting. All right. Let's see, what else have I got here? I don't have a whole lot else, actually. Sure. Let's go back a little bit, and I'm going to do some questions that might be helpful in some other ways. So let's say I flip 10 coins. What's the probability of either 0 heads or 1 head? Okay, well, let's talk about how many things are in the sample space. All right, so again, right, the probability of a thing sorry, there's a thing I wanted to say about the previous thing, but it's not that important. The probability of finding 0 heads or 1 heads is the number of ways of getting 0 heads or 1 head divided by the number of ways to flip 10 coins. Can anyone tell me how many ways are there to flip 10 coins? You should be thinking about using an exponent or a power to do such a thing. Thanks, Shanna. Shanna came up with 1024, which you could also, and it's probably easier to write just as 2 to the 10th power, right? You have two choices for each coin. 2 times 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 2 is 2 to the 10th, which is 1024. So there are 1024 ways of getting of flipping 10 coins. How many ways are there of getting 0 heads? 1. Or if you prefer, 10 choose 0. There are 10 choose 0 ways of getting 0 heads. And that's equal to 1. Somebody else should be able to tell me how many ways are there of getting 1 coin. Well, sorry, 1 head. Flip 10 coins. This is where I wish we were in person, so I could be like, hey, you guys know this, and you would have to look me in the eyes and be like, I don't want to disappoint James because he's waiting for me to say something. But here, I'm just looking at pictures. It is definitely 10 choose 1, which is just 10. Right? If there's 10 coins, there's exactly 10 ways you can get 1 head and the rest being not heads. The first can be a head, the second can be a head, or the third can be a head, or the fourth, and so on. So, right, and in general, if someone says, if you flip X number of coins, and someone says, how many ways can you get so many heads? It's just X choose that number. So if I asked how many ways can you get 6 heads, the answer would be 10 choose 6. So here, number of ways of getting 1 head is 1 plus number of ways of getting, sorry, 1 head is 10 and 0 heads is 1 for a total of 11 out of 1024. So that's the probability of getting 0 heads or 1 head. It's the number of ways of getting 0 or 1 head divided by the total number of ways of flipping 10 coins. Cool. And again, right, this here is your 2 to the 10. Let's look at something else. Sure. This is kind of maybe a review that might be helpful for the quiz you guys have. How many distinct ways of rearranging the letters in the word statistics? Statistics. First of all, how many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 letters. So there are 10 factorial permutations of those letters, but some of them are repeated. There are 1, 2, 3 S's. So for all 10 factorial possible permutations of these 10 letters, 3 factorial of them will have the S's in like the same spots, right? Like maybe you have the word statistics where the first S is here, the second S is here, the third S is here, and maybe you also have the word statistics, right? Where the second S is there, the first S is there. Those are getting counted differently in your 10 factorial, but we don't want them to. So we have to divide by all the ways you can permute those 1, 2, 3 S's, which is 3 factorial ways. All right, and there's also 1, 2, 3 T's, and there are 3 factorial ways of permuting them. And there are also 1, 2 I's, and there are 2 factorial ways of permuting them. And there's 1 A and 1 C. We don't have to divide by 1 factorial and 1 factorial, it's just 1. So this would be the number of distinct ways of rearranging the letters in the word statistics. We got time. I suppose we could also answer. No, I don't know. I guess we could. Let's see. What do I want to say here? I want to know what's the probability of a word beginning with at least one A. Sorry, not one A. There's only one A. It's not very exciting. At least one S. Okay. Well, we know that this is the total number of distinct words. How many distinct words end with S? Yeah, this seems like a harder question. Still not possible though. So, we want to find, so basically the idea is now we want to find the number of distinct words that begin with an S. So we're going to put an S in the first spot, and then the other 9 spots, you have choices. So there's now 9 factorial ways of rearranging all the other things, right? So the number of these words, the number of these distinct words is going to be 9 factorial divided by, again, the number of ways you can rearrange the S's and the T's and the I's. So still a 3 factorial times a 3 factorial times a 2 factorial. And then if you divide this by that, well, that's going to actually come out to be really nice. 9 factorial over 3 factorial, 3 factorial, 2 factorial, divided by 10 factorial over 3 factorial, 3 factorial, 2 factorial. The 3 factorials all and the 2 factorials cancel. 9 factorial over 10 factorial is just 1/10. So it looks like there's a 1 in 10 chance of your word starting with at least one S. I feel like that feels kind of wrong. Like it might be right, but it doesn't, it feels like too easy. Yeah, it really does feel too easy. I'm gonna need to think about this more because I'm not 100% positive I've said this the right way. So I would not quote me on this just yet because it feels like I'm missing something here. I'll think about that for a minute after class, after office hours. And if I come up with something, well, once I figure out if something different or if this is actually correct, I'll take a look at that and I'll write something on Canvas for you guys. Just because this just feels like it should be. It feels not right. That's all I can say. Sometimes when your answer feels too easy, you're kind of like, I don't know about that. Let me do one more. You take a 5-card hand. What's the probability of getting? I don't want to say it that way. Of getting 3 kings and exactly 2 other cards, meaning 2 other non-pair. So basically, the question I'm really asking is, what's the probability of getting a 3 of a kind with a 3 of a kind or kings? So to have a 3 of a kind in poker, you can't have a 4th king. That would give you a 4 of a kind, and you can't have 2 other cards that are a pair because that would give you a full house. So what's the probability of getting a 3 of a kind with kings? Well, whenever you're talking about a 5-card hand, you're always dividing by 52, choose 5. So how many ways can I get 3 kings? Well, there's 4 kings to choose from, and I'm choosing 3 of them. There are 4, choose 3 ways of getting 3 kings, which is just 4, right? There's 4 different ways of getting 3 kings. Basically, there's 4 different ways of excluding 1 king. And then 2 other cards. Well, I can pick anything that's not a king. So there are 12 other types of cards that are not a king. So there's 12 choose one ways of picking one other rank of card times 4 choose one ways of picking. Ooh, actually, I think I want to do this. I think I'm doing this wrong. Not that wrong, but a little bit wrong. Yeah. So there's actually a problem with what I'm doing here. I was going to do it this way: 11 choose one, then times 4 choose one. But the problem with this is that you could pick, like, say, a queen and then a jack, or a jack and then a queen, and you would count them as differently. And we shouldn't count them as differently, because I don't care if it's what, I don't care what order the cards come in. So what I should actually be doing here is saying, for the two other distinct ranks, there are 12 choose two ways of picking them. And then for each of the ranks I pick, I'm going to do a 4 choose one to pick the suit, and a 4 choose one to pick the suit. So this is the probability of getting exactly 3 kings and 2 other cards that aren't a pair and aren't a king. Okay.